After years of speculation and research, scientists have made an astounding breakthrough: the discovery of the first ever white hole. This finding has sparked excitement among astronomers and holds implications for individuals like you. Join us as we delve into the fascinating world of white holes, exploring what they are, why astronomers are thrilled, and how this discovery affects us. Black holes, those massive and ominous entities lurking in the depths of space, have captured our imaginations. However, there exists a contrasting counterpart known as a white hole. While equally awe-inspiring, comprehending white holes requires an understanding of black holes and their origins. Let's begin by familiarizing ourselves with black holes, as many of the descriptions apply inversely to white holes. Black holes come in various sizes, but three primary types exist. The classification of a black hole is determined by its mass and size. The smallest type, known as primordial black holes, is believed to be as tiny as a single atom, yet possessing the mass equivalent of a large mountain. Moving on, we have stellar black holes, which are the most common medium-sized black holes. They can weigh up to 20 times more than our Sun but are relatively compact, fitting within a sphere with a diameter of approximately 10 miles. These black holes owe their immense gravitational pull to their dense mass concentration. Within our Milky Way galaxy, scientists estimate the presence of dozens of stellar black holes. Finally, we have the behemoths known as supermassive black holes, outweighing 1 million suns combined. Astonishingly, these colossal entities could be contained within a sphere no larger than our solar system. Evidence suggests that every large galaxy harbors a supermassive black hole at its center. At the heart of the Milky Way galaxy lies a supermassive black hole named Sagittarius A with a mass equal to approximately 4 million suns. It could be encompassed within a sphere similar in size to our Sun. Now, let's explore the origins of black holes. Primordial black holes are believed to have formed shortly after the Big Bang during the early universe. Stellar black holes, on the other hand, come into existence when the core of a massive star collapses upon itself, triggering a supernova, an explosive event that propels fragments of the star into space. Scientists propose that supermassive black holes and their host galaxies develop concurrently. The size of a supermassive black hole is closely tied to the dimensions and mass of its galaxy. Although black holes cannot be directly observed due to their gravitational pull being so strong that even light cannot escape, scientists can detect their influence on surrounding stars and gases. By studying the motion of stars in relation to a specific point in space, scientists can determine if they are orbiting a black hole. When a black hole and a star are in close proximity and orbiting each other, the interaction generates high-energy light. Advanced scientific instruments can detect this radiation. In certain cases, a black hole's gravitational force is powerful enough to strip a star of its outer gases, leading to the formation of an accretion disk, a disk of matter swirling around the black hole. As this matter spirals towards the black hole, it heats up and emits X-ray light in all directions. NASA telescopes measure this X-ray emission, providing valuable data for astronomers to investigate the properties of black holes. Now, let's address a common question: will our Sun ever transform into a black hole? The answer is no. The Sun lacks the necessary mass to collapse into a black hole, thereby ensuring its salvation. However, this doesn't mean that the Sun will evade its inevitable demise. In billions of years, as the Sun reaches the end of its life, it will expand into a red giant star. Eventually, it will shed its outer layers, forming a luminous ring of gas known as a planetary nebula. Ultimately, all that will remain is a cooling white dwarf star. Nonetheless, these events are far in the future, so worrying about them at present is unwarranted. Let's delve into the concept of white holes. Unlike black holes, white holes are their exact opposite. In fact, they can be thought of as black holes observed in reverse, going back in time. As previously mentioned, once matter crosses the event horizon of a black hole, it becomes trapped due to the overwhelming gravitational pull, making escape impossible. Similarly, a white hole represents a region where space-time continuously flows outward. It possesses an event horizon radius that forbids the entry of any matter, including light. It is believed that white holes emit light with the same intensity as the force exerted by a black hole. If a daring crew were to attempt entering a white hole, the sheer power of the gamma rays emitted would annihilate both them and their spacecraft. Even if we were to imagine a ship sturdy enough to withstand such energy, the structure of space-time around a white hole is arranged in a way that the closer one gets, the greater the amount of acceleration required to enter. To put it succinctly, accessing the interior of a white hole necessitates more energy than what exists in the entire universe, making any attempts futile. As you may suspect, the concept of white holes originated from the fascination with black holes in mathematical theories. In 1905, Albert Einstein made a significant realization. While observers undergoing acceleration experience time differently, this principle does not apply to non-accelerating observers, those who move at a constant speed or remain stationary. Additionally, Einstein's theory of general relativity, published later, proposed that objects with mass create a gravitational field that distorts both time and space, rather than acting as a physical force. Karl Schwarzschild utilized Einstein's field equations to solve for the equation of mass in empty spacetime, which refers to an area completely devoid of matter. This endeavor led to the development of the Schwarzschild metric, which we won't delve into due to its inherent complexity. In simple terms, it serves as a mathematical representation of a black hole. Schwarzschild successfully formulated an equation for a static black hole devoid of charge or change. This represents an external black hole that remains unaltered in size and has existed indefinitely. It's important to note that events occurring at or beyond the event horizon of a black hole are projected infinitely far into the future. As a result, from the perspective of an external observer, these events never actually transpire. The Schwarzschild metric reveals that in an idealized black hole, space and time interchange their roles, effectively transforming space into time and time into space. This concept shifts the singularity of the black hole to an inevitable future time, rather than a specific location. When reversing time within a real black hole, we observe a dying star. However, when reversing time within an eternal black hole, we encounter a white hole. Nevertheless, not all scientists concur on the existence of white holes. This skepticism adds significance to the recent discovery regarding white holes. Some scientists argue that although white holes comply with general relativity and possess mathematical validity, their practicality remains questionable. This skepticism has led some scientists to label white holes as an impossible possibility, implying that while they cannot be entirely disregarded, their observation through telescopes is not anticipated. These scientists contend that white holes violate the second law of thermodynamics, which stipulates that the entropy within the universe either remains constant or increases. Entropy is commonly described as chaos but can be better understood as an increase in the number of possible states for particles within a given system. To illustrate, imagine a house reduced to rubble. This scenario exemplifies an increase in entropy since the rubble can be used to construct various other structures such as sheds, bookshelves, mounds, and paper. Nevertheless, it's crucial to recognize that a house represents just one specific state of those particles. While small, localized decreases in entropy can occur, the overall entropy of the universe must continue to increase. Black holes excel in this aspect, as they capture low-entropy matter like planets and disperse them across vast spaces over time, augmenting the chaos of space. However, white holes, which expel matter, violate this fundamental law by reducing the overall entropy. This is precisely why physicists argue against the possibility of time flowing backward. However, this does not conclusively prove the non-existence of white holes. Let's consider the proposition put forth by theoretical physicist Carlo Rovelli. According to Rovelli's suggestion, once black holes can no longer evaporate and shrink due to the limitations imposed by spacetime, they undergo a quantum bounce, experiencing an outward pressure that transforms them into white holes. Essentially, black holes instantaneously transition into white holes upon this transformation. However, as external observers, we continue to perceive them as black holes for billions of years due to the time dilation caused by gravity. If this theory holds true, black holes that originated in the early stages of the universe might be on the verge of their demise, ready to burst forth into cosmic rays or other forms of radiation at any given moment. We may have even witnessed such an event back in 2006 when NASA's SWIFT satellite detected an extraordinarily powerful gamma-ray burst named GRB 060614, originating from a highly peculiar region of the sky. Typically, these bursts fall into one of two categories: short bursts or long bursts, often associated with supernovae. However, GRB 060614 defied these categorizations. It persisted for an astonishing 102 seconds, yet it was not linked to any stellar explosion. For comparison, most gamma-ray bursts last only between 2 and 30 seconds. Furthermore, GRB 060614 occurred within a galaxy that housed very few stars capable of producing explosions or long bursts. To astronomers and astrophysicists, it seemed that this gamma-ray burst emerged seemingly out of nowhere, only to swiftly collapse upon itself after a brief duration. However, several years later, scientists proposed the intriguing hypothesis that GRB 060614 could have been a white hole. What led them to this conclusion? It's because GRB 060614 perfectly aligns with what one would anticipate from a white hole, an immensely unstable fountain of matter and energy that vanishes shortly after its formation, typically originating from a point too minuscule to be observed. What strengthens this hypothesis is that current scientific models fail to provide an alternative explanation for the occurrence. We invite you to share your thoughts on the existence of white holes in the comments section below.